All right, this video is going to go over Bonding 2 worksheet. Before we grade this assignment, if you were in class, I would ask you to do a couple of things before we grade it. The first thing that I would ask you is, did you find the 4 exceptions? You should have had 4 exceptions, which means you had to be careful with the B's and look for expanded octet, so hopefully you found the 4. The next thing is, we learned about polyatomic ions, and we said that when you see a polyatomic ion, you want to include brackets and charge. And then the last thing that we looked at outside of bond length and strength was the idea of resonance, where the electrons move back and forth between the double and single bonds. So there has to be a double bond, a single bond, and all the atoms attached to the central atom have to be the same. There's definitely resonance on this homework, so hopefully you found those all. If you need to make some changes before you grade, that's okay, right? But now it's going to be out of 60 points, so please make sure you grade this on correctness, and then you're going to show this to me the next time I see you in class. So it's out of 60, and you have to grade in red. So make sure that you have a red pen and you're grading it correctly. So remember, the structures are worth 2 points all or nothing. So here we go. This first one's worth 5 points. You definitely have to have brackets and charge because it's a polyatomic, 8 available electrons, O single bonded to the H, and then 3 lone pairs. This is worth 2 points all or nothing, no resonance. SiS2, 16 available. The Si has 2 double bonds, and each S should have 2 lone pairs. No resonance. This one here is a polyatomic, so you're going to go ahead and have brackets and charge. That's worth 1 point. 24 available. Each structure, the first structure is worth 2, and then this one's worth 1, and this one's worth 1, and each arrow is worth a half, so it's a total of 1 there. Yes, it has resonance. Here's a double bond. Then here, then here. It doesn't matter where you put them. It's just you have to have a double bond on each oxygen as you show all resonating structures. pH3 has 8 available. Phosphorus is in the middle. 1 lone pair, 2 bonded pairs to H's. That's worth 2 points. No resonance. Beryllium is your first exception. 4 electrons. Remember, you got to be careful with the B's. Beryllium is actually a metal. It's okay with just 4 electrons or 2 bonds. No resonance. Last one here. Ammonium is a polyatomic, so you need brackets and charge worth 1 point. 8 available. Structure has an N single bonded to 4 H's. That's worth 2 points. No resonance. Please write how many you missed in the bottom left-hand corner. Moving on to the back. You have S3, 5.5 total points here for this first one, 18 available, worth 1 point. S3 has the S in the middle and then 2 attached. This does have resonance because it's single, double bond, right? And all the things attached are the same. You have to have 3 lone pairs on the single bonded S and 2 lone pairs on the double bonded S that's attached. Half a point for the double-sided arrow for resonance, and yes, it does. So that's worth 1 point. Down here, this one's an exception, 24. BCl3 has 3 Cl's attached. No resonance. Remember, careful with the B's. Capital B is boron, which is a metalloid. It's happy with 3 bonds. So far, I haven't talked about this, but let's say you forgot to put the yes and no. Don't mark it wrong. Obviously, if you said no here and it did have it, then you have to mark it wrong, right? But if you left, for example, this one blank and you didn't put anything there, then I would consider that a no, all right? But in the future, make sure you're reading the directions, okay? PCl5 is an exception, 40 available. Remember, phosphorus can hold more than 8 electrons because it's in the 3rd energy level, and it can put some in the D sublevel, 3D. So you have 5 Cl's attached. All of them have 3 lone pairs, no resonance. This one here, another expanded octet exception, 48. You put all 6 CLs onto the S. S can hold more than 8 because it has a 3D sublevel to put more electrons. No resonance. CN1 minus is cyanide. This one has a triple bond and then a lone pair on each atom. No resonance, 10 available. And then carbonate has 24. 2 points for the first structure, 1 point for each of the remaining resonance structures, half a point for each double-sided arrow. Brackets and charge are worth 1 point, so it's just one time. And then make sure that the double bonded O's have only 2 lone pairs, single bonded have 3 lone pairs. So then that's this back page. Make sure you write how many you missed in the bottom left-hand corner. And then please have your score out of 60 points on the top of this page. So first thing we're going to look at is some definitions of molecular orbitals. Molecular orbitals is the idea that, yes, we have atomic orbitals like the S, P, D, and F, right? But when the atoms, right, of the 2 different elements combine, right? So for example, maybe something like this, right? An H, so this would be the H and this is the Cl. When these 2 combine, right, they have their own orbitals, like the S, right? And this one, because it's a halogen, would have S and P, right? Somehow when they mesh together, right, they're going to have their own orbitals, all right? So when they overlap on the bonding axes, so that would be along here, right, that's called a sigma bond. So this is a definition you need to know for the test. A sigma bond is a bond formed when 2 atomic orbitals overlap, specifically bonding axes, okay? And we use the Greek letter sigma, so it just looks like this, okay? What does that look like? Once again, if I have this atom and this one over here, right? If I were to look at the electron clouds, it would form a blob along the x-axis. So just like this, okay? This one, though, has 2 of the same. So maybe a better example of this would be showing you something like H2, where the 2 electrons, right, are being shared between the 2 atoms. Now, the p orbitals on separate atoms are a pi bond. This is another definition you have to know for the test. It's a bond formed above and below the bonding axes of the bonded atoms. It's considered a pi bond. They tend to be weaker than sigma because they're not overlapping on the bonding axes. So remember, we have px, py, pz orbitals, and what they're saying is these electrons that are overlapping, they're overlapping above and below the bonding axes. So very different from the one up here, right? And so these aren't as strong, and those are called pi bonds. These are going to happen when you have multiple bonds. So you do have to know this chart for the test, all right? When it comes to sigma and pi bonds, if you have a single, double, or triple, you have to have an overlap on the sigma on the bonding axes because the atoms have to attach. So whether I have a single, double, or triple, they all have 1 sigma bond. And when it comes to pi bonds, right, a single bond has 0 pi, double has 1, triple has 2. So now we're going to look at some examples and figure out the number of sigma and pi, okay? And you have to be able to do questions like this for the test. So I'm just going to put TQ so that you know that you are responsible for knowing how to do doing these types of problems. So here I have HCN. This is a single bond, right? So it has 1 sigma and 0 pi. Here I have a triple bond. This triple bond, right, has 1 sigma and 2 pi. And that's all we have for bonds. So the total number of sigma here would be 1, 2. And the total pi, 0 pi plus 2 pi is 2. That's as hard as it gets. So let's look here, right? For this one, it's a single bond, 1 sigma, 0 pi. This one here, 1 sigma, 0 pi, because they're single bonds. This here is a double. The double has 1 sigma, right? 1 pi. So now how many total do I have? For the sigma, 1, 2, 3. Pi, 0, 0, 1 is a total of 1. All right? Now, the last thing that we have to learn today is actually us looking at what are the shapes of these molecules. So in my room, above the lab tables, I have these structures where you can see how the atoms are going to actually look when they're connected to other atoms when there's a central atom. All right? So how do I know what the shape looks like? There's something called VSEPR, which is short for valence, shell, electron, pair, repulsion, theory. So it predicts the three-dimensional geometry of molecules. We know valence shell means the outer electrons, right? Electron pair repulsion is the idea that electron pairs try to get as far away as possible. Yes, all atoms are going to work together to get their 8 on the outside whenever possible. But that doesn't mean, right, that they just combine together. These are electrons and they don't like each other. So what we can do is determine the angles of the bonds. And what we have to know is that there's bonding pairs that form bonds, and then there's lone pairs, which are non-bonding pairs. And what I'm going to tell you is that lone pairs reduce the bond angle between the atoms. Lone pairs reduce the bond angle between atoms. So, lone pairs repel more strongly than bonded pairs. So let's say I have an element here. Let's say that this is X, right? And there's a lone pair on it. The lone pair pushes these bond angles down. So this here is the bond angle. Now, how do I know what is the shape? The first thing is you have to draw the Lewis diagram. You got to draw the Lewis dot structure, and you have to draw it correctly. So draw the Lewis diagram correctly. That's really important, because if you draw it wrong, there's no point in looking at the shape because you don't have the right structure. So then you have to tally up the number of pairs on the central atom. Whether it's a double or a triple bond, it counts as one thing attached. The shape is determined by the number of bonding pairs and lone pairs. So that's what we're going to look at here. All right? So, all right, there's a couple of examples here that aren't discussed, and I'm going to be adding these. All right? So let's just look at something like H2 and Cl2. So H2 looks like this, and HCl looks like this. The shape of these two is linear. So why is it linear? Because it looks like a line, right? Straight across. So anytime I have just two things attached, they're straight across. So this is HCl, and this is H2. All right, you're going to be working with these bonding kits, and so the white always represents an H, the green represents a halogen. All right, so here Cl, if I had HF, HBr, they would all look the same because they'd all have a green atom there. All right, but the first example we're going to look at that's truly linear based on this information is that we have two things total attached to the central atom. 2 bonded and no lone pairs. So that first example is BeH2, and that looks like this one, right? If I have a central atom with no lone pairs and 2 things attached, it's going to be straight across, which is called linear. So that is the first one that we need to know, the linear shape. I'm going to give you another example to look at here, CO2. Now remember, CO2 is actually this structure. So this is the structure for CO2. I like to show this one because I want you to recognize, right, that we count a double bond as just one thing attached. Do you see here it says double, triple bonds count as just one thing attached? So, because what we want to look at is what is the shape around the central atom. I don't care, right, what it looks like over here or what it looks like over here. I care about what it looks like from the middle, all right? So this is another example that's linear because the atoms are straight across, all right? So we've looked at the linear shape, and we know that that's going to happen when we have 2 things attached to a central bond, right? And there's no lone pairs on the central atom, okay? Now, the next thing we're going to look at is what if I have 3 things attached? So 3 total things attached, 3 are bonded, and no lone pairs, right? Because the atoms want to be as far apart as possible, right? It's going to look like a Y. So here is BF3. BF3 looks just like this. So when I draw this, right, when I draw BF3, I cannot draw it like a T, because if I draw it like a T, these are going to come in closer, and that's not what we want. We want to spread them out as much as possible. You know that a circle is 360. 360 divided by 3 is 120, so these are going to be the bond angles. For the linear, it's 180, right? But for trigonal planar, so that's our new name, it's called trigonal planar because planar means flat. When you took geometry, or if you're in geometry now, 3 points on the same surface makes a plane, right? So here's my 1, 2, 3, right? And so that's going to be trigonal planar. Another example of trigonal planar would be SO3. We drew this yesterday. That one looks like this. Yes, this does have resonance, but for the sake of notes, I'm just going to draw one of them, okay? But because we know that electrons need as much space as possible, you can no longer draw it like this. So I would not give you credit for the shape if you drew it like a T. You cannot draw it like a T because you want to give these pairs as much space as possible. So we've looked at linear and trigonal planar. Now we're moving on to the back. So now we have at the top SO2. So before today, some of you may have drawn SO2 to look like this. Now remember, VSEPR, valence shell electron pair repulsion, cares about what is the shape around the central atom. I don't care what the shape is here or here. I'm just defining the shape by the middle atom, okay? So now, before today, we drew SO2 like this. But we learned over here that lone pairs need more space. So what I like to do is I like to draw almost like a little balloon around any lone pairs on the central atom. I'm not going to put the balloons on these just on the central atom. And the reason why I do that is because that reinforces to me that these lone pairs need more space than these bonding pairs. So the point is that I cannot draw it like this anymore. I have to draw it, right, so that these lone pairs can have more space. And so what that's going to do is push the bond angle to be smaller. And so it's going to have this shape, which is called bent. This bond angle, right, is almost like 1, 2, 3 things attached. So there's 3 total. 2 are bonded. Remember, we count the double bond as just 1 thing attached. And there's 1 lone pair. That 1 lone pair pushes the bond angles in, right? So I can no longer draw it linear because it's not linear. I have to draw it bent. Okay? So what would that look like? That's going to look like my structure here. It would look something like this. Okay? So we have SO2, right? And up here would be the lone pairs that take up more space. It is not linear. Even if I want to make it linear, right, it's going to move and go back to a bent shape. So that's the nice thing about this molecule kit. If you're using the right atoms to represent the molecules, it's going to naturally make the shape that it's supposed to. Okay. The next one that we're going to look at is 4 total things attached, right? So this one was bent, sorry. 4 things total attached, all bonded, no lone pairs. So that Greek prefix of tetra is coming back. This is called tetrahedral, all right? Tetrahedral has this shape. It looks like this, right? It is not flat because there's a top, right? And as I move it, you can tell that it's 3-dimensional. So what does that look like? So far, we've been drawing it like this. CH4 to look like this. But that's not true because it has a bond angle of a little less than 109.5, and that makes it 3-dimensional. Remember, these electrons are taking up as much space as possible. So the best way to do that is for it to be in 3D, not 2D. But I'm okay with you drawing it this way. And the reason why I'm okay with you drawing it this way is because it's going to help you to understand polarity when we get to that point in about 2 days in the notes, okay? But how would I draw this 3-dimensionally? Okay, I want to show you how to do that, but I first have to take apart the actual molecule. So here, notice how there's 3 things flat. So the way that I would do that is I'd put my carbon in the middle, 1 H there, and 1 H here. So that would be that part. Now, how do I draw the one coming out of the page, right? That would be this one coming out of the page. To do that, I make a filled-in wedge. So just like that. And now how do I draw the one going behind the page? Right? So it looks like this. How do I draw the one going behind the page? I make a dashed H like that. So that's what it looks like 3-dimensionally. Okay? Once again, you can keep writing it like this. What you have to know is 4 things attached is tetrahedral. Now we're going to move on to 4 things total. Then in this case, we're going to have 3 bonded and 1 lone pair. Okay? So The example that we have here is NH3. NH3 looks like this, or it used to. We used to draw it like this, and I said that it didn't matter, right? But it does matter, because remember, we care about what the shape looks like around the central atom, the middle one. So anytime I have a lone pair on the central atom, it's going to push the bonded pairs in together. So it doesn't look like a T. I cannot draw it like that. I will not give you credit for the shape if you draw it like that. The shape of NH3 is actually called trigonopyramidal. And the reason why is because it doesn't lay flat on the table, right? It looks like a pyramid. If I hold it like this, right? It looks like a pyramid, and there's 3 points that touch the surface, right? Very different from trigonoplanar. Trigonoplanar is the one on the other page, right? This one is flat. This one is not. You can see that they're not flat if I hold them like this too, right? Like if I hold them to each other. These are all flat. This one's not. Okay? So I have to draw it like a pyramid. So the way that I want you to draw it now, so either one of these is okay for tetrahedral, but for trigonopyramidal, if you write pyramidal, I want it to look like a pyramid. So it should look like this. Do you see how that better represents a pyramid, right? These are closer together because this lone pair needs more space. And I don't need you to show like wedges that are filled in and dashed, but technically this one should be dashed and one should be filled in, but I'm okay with this, right? So you either draw it like this or N, H, and it doesn't matter like which one is filled in, dashed, or wedged, right? But you're gonna draw it this way now. It has to look like a pyramid, okay? The next one, H2O, is a big deal, all right? If you're gonna leave chemistry with one main thing, well, second main thing, right? Because I think it's also important for you to know that chemistry occurs because of electrons, right? The other thing is water, right? We have drawn water to look like this. And that's not correct because water is bent. All right. That one's trigonopyramidal again. Okay. Now we're looking at bent. So why is it bent? Because lone pairs need more space. So here we have 4 things around the central atom. 1, 2, 3, 4. 2 are bonded and 2 lone pairs. Now, this is what water looks like. Water is bent. Water is bent. Know that, okay? So why is water bent? Because we have 2 lone pairs, and sometimes students say, well, why do we draw it like this if lone pairs need more space? Because you have to look at it 3-dimensionally. So if I turn it this way, okay, do we agree that we have all this space over on this left side and all this space on the right side for the electrons to hang out? And that's actually what happens. I think this picture is going to give it more justice than what we're going to do. Okay, so 2 bonded pairs, 2 lone pairs, it's going to give it a shape called bent. So how are we going to draw it? Like this. It still has the 2 lone pairs, but we draw it bent. And this looks bent, right? Doesn't look linear. We cannot draw it linear. Remember, when it comes to these, like a balloon around the lone pairs, it's because it's the lone pairs on a central atom, not an attached atom. Okay? The last two are pretty easy because these are the exceptions. And so this is the shape no matter what, because these are the only possibilities when you have 5 or 6 things attached. So this is 5 total, 5 bonded, no lone pairs. 6 total, 6 bonded, no lone pairs. So PCl5. PCl5 is called trigonal bipyramidal. So now with trigonal bipyramidal, so I'm going to show you what that shape looks like. This is trigonal bipyramidal. The reason why it's called trigonal bipyramidal is because trigonal comes from this plane here where there's 1, 2, 3, trigonal, right? And then bipyramidal, because if I were to connect all the vertices, right, and make faces on here, you have a pyramid on top and a pyramid on the bottom. So this is called trigonal bipyramidal. I'm not going to expect you to know these bond angles, but you do have to know the names, right? I don't give you the names on the test. You'll know them. Trust me, we're going to do enough practice. You're going to know them, okay? So this is trigonal bipyramidal when 5 things are attached. So how am I going to draw this? All right. Well, I want to make sure that I show the trigonal part. So I think the easiest way is to make my trigonal part that way. Add my lone pairs, right? And then I have the CL coming out of the top of the page and then going behind the page. Okay, so that would be it looking like this, right? So I have my triangle, right? And then one going down the page and one coming at me, which would be this one. So now we look at the last one, 6 things attached. When I have 6 things attached, that's called octahedral. So students always say, well, why is it called octahedral if 6 things are attached? Well, the reason why is because if I connect all the vertices on this structure, I'm going to have a face here, 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 and here. So there's 4 faces on top, 4 on the bottom. 4 plus 4 is 8, and that's why it's octahedral. So how am I going to draw this? I think the easiest way to draw it is very similar to this picture here. So we do S with the F's like this all on the same plane. Don't forget your lone pairs. And then I draw one coming out of the page. And one going behind the page. Okay? So let's recap, right? This here is octahedral. 6 things total, 6 bonded. This one, trigonal bipyramidal. 5 things attached, no lone pairs. Here, this one's bent. 2 lone pairs, 2 bonded pairs. And yes, there is another bent up here. 2 out of the 3 special ones that have lone pairs are bent. So that's going to be easy to remember. This one here, though, is called, trigonal pyramidal. So this one here, trigonal pyramidal. And then the last one here is tetrahedral when all 4 things are attached. Okay? So then on this page, we learned about linear. Linear is the easiest way to put 2 atoms. That gives them as much space as possible. And that would be the same if I have 1 central atom and 2 things attached, no lone pairs. If I have a central atom and 3 things attached, no lone pairs. This is called trigonal planar. So now we're just going to take a minute to practice. We're going to go back to a page that we already did in the notes. We're going to look at page 5. All right. So let's see if we can figure out what the shapes of these are. 2 things attached, no lone pairs, so this is going to be linear. This one here, 2 things attached, no lone pairs on the central atom. Yes, they have lone pairs, but we don't care about those. We care about what does it look like when 2 things are attached. This one's also going to be linear. HBr, 2 things attached, that has to be linear also. This one here, 4 things attached, no lone pairs, that will be tetrahedral. This one here, NH3, we have this lone pair. So now I can't draw it like that anymore. I would have to redraw this and draw it like a pyramid. So this one has a shaded in wedge, dash wedge, and then a single wedge, right? This one here, 2 lone pairs. So anytime I have a lone pair, right, I have to change the shape. I can no longer draw it this way. It's going to be bent because I have these 2 lone pairs here that are going to push these down, right? So technically maybe more like this. I feel like those aren't bent enough, okay? This one here, 2 things attached, linear. This one here, we actually did CO2, that's also linear. This, the carbon around each carbon would be tetrahedral. This one here, on the central atom, there's no lone pairs, so the best way to separate 2 things attached would be linear, okay? So now, what is your homework? Your homework is to do bonding 3. It says here, for this assignment only, if the structure has resonance, you only have to draw 1 in this column. And then you have to tell me what is the name of the structure, and it must be drawn to shape. So you draw it to shape here. So if you tell me that it's trigonal planar, right, it has to look like a Y, right? If it's tetrahedral, you can keep drawing it like a X, right? If you want, bent should look bent. Trigonal pyramidal should look like a pyramid. Trigonal bipyramidal is going to have that triangle in the middle and then it coming out of the top and the bottom. And then we have octahedral, which has the 6 things attached. Now, I'm going to give you a hint. You've done all of these structures. You've done all of these structures in bonding day 1 and day 2. Hopefully, though, you took the time to draw the right structure because now what you're going to do is you have to have the right structure to know the right shape. So hopefully you did that correctly, and then using your homework is going to help you. This should not take you that long if you have the correct structures. If you feel like you need more practice on drawing structures, you should have the right answers in your homework because you've graded it correctly. Go back and see if you can get them correct now. All right? So make sure you turn this in on Google Classroom. If you have questions, please feel free to email me. Thank you.